Hello, in this video I'm going to explain how you can calculate the motion of a mass moving in the resultant gravitational fields of two massive bodies. So we have here the Earth, which will create a gravitational potential around it, and the potential is most negative on the surface of the Earth, and it increases towards zero as we move away from the Earth. And on this side, we have the Moon. The Moon on its own will also create its own gravitational potential around it. And the potential is also most negative on the surface of the Moon, and it increases towards zero as we move away from the Moon. You know, I'm really fond of visualizing the gravitational potential well created by massive bodies. So there's a deep one created by the Earth, and a shallow one created by the Moon. So what is the resultant gravitational potential landscape? The red line here shows the resultant potential. We are just adding up the individual potential of the Earth and the Moon at every point. So for example, this plus this is this. This plus this is this. This plus this is this, and so on. Remember, gravitational potential is a scalar, so we are just doing a scalar summation. We don't have to bother about any direction, just add up the two numbers. You know, I really like this visualization of the potential landscape because mathematically we know that the gravitational field strength is the negative of the potential gradient. But intuitively, I'm sure that you can see that because the gravitational landscape here is flat, the field strength here has got to be zero. The point where the resultant potential is flat is the point where the gravitational field due to the Earth and the gravitational field due to the Moon are equally strong, and they cancel out, and this is the null point. On the left of the null point, you see the gravitational potential landscape sloping down this way. That means the resultant gravitational field must be this way. Likewise, on the right side of the null point, you see the gravitational potential landscape sloping down towards the Moon. So on the right side of the null points, the resultant field must be pointing towards the Moon. In fact, the steeper the landscape, the stronger the field. The flatter the landscape, the weaker the field. Let's put in some numbers. Let's say the resultant potential on the surface of the Earth is negative 62.3 megajoules per kilogram. On the surface of the Moon is negative 2.6, and the maximum potential, the potential landscape, peaks at negative 1.3 megajoules per kilogram. Suppose I want to throw a stone from the surface of the Moon. At what speed must I throw the stone such that it can arrive back on Earth? As the stone makes its journey towards the Earth, initially it will be slowing down because the resultant field is towards the Moon. So it will slow down, but if it manages to reach the null point and beyond, then the resultant field will have switched towards the Earth, and you can count on the gravitational pull to accelerate the stone all the way back to Earth. So the crucial thing is really whether the stone is able to arrive at the null point. To solve this problem, we are going to use the principle of conservation of energy. The initial position will be the surface of the Moon, and the final position will be at the null point. So as the stone is making its journey, it's just trading its Ke for Gpe. Therefore, at any position, the summation of Ke and Gp should be a constant. We are going to write the initial Ke as half mu squared, so small m is the mass of the stone. Its initial Gpe, when it's on the surface of the Moon, can be written as the mass multiplied by the gravitational potential, which is negative 2.6 megajoules per kilogram. After all, gravitational potential is Gp per kilogram, right? So if you take the Gp per kilogram multiplied by the mass, you'll get the Gpe of the stone. So the final Ke, at the null point, we are going to write it as 0 because we want to find the minimum launch speed such that it can arrive at the null point. And its Gp at the null point will be the mass times the gravitational potential there, which is negative 1.3 megajoules per kilogram. So press your calculator, you'll arrive at the answer of U being 1610 meters per second. So if you are ever stranded on the moon, well, you just have to jump off at this speed, about 1,600 meters per second, and then we'll welcome you back home on Earth. Okay, see you.